Assalamu alaikum wa rahmatullahi wa barakatuh. Peace be upon you all and welcome to the channel. In this video we will discuss, or rather we will create, the adjacency list graph. Previously we have discussed the two types of graphs, adjacency list and adjacency matrix. For this video we will design the adjacency list graph bi'idhnillah and God willing, and it will be the unweighted and undirected graph. In later episodes, inshallah bi'idhnillah and God willing, we will design the directed graphs. And with that, let us start. I will design two classes in addition to the driver class. One for the vertex, the other will be for the actual adjacency list graph itself. I will create a class here and I will call this vertex. The design will mimic that of the tree that we covered previously. At least, what did we cover? Binary search tree? Ah, yes, the binary search tree. It will follow a similar approach. For the tree, we designed the node in its own class and the tree in a separate class. The same will apply here. We will design the vertex in one class and the graph in another class. You will need two components. You will need the data type of the data being stored in each vertex, and you will need a list of these vertices or vertexes. Because remember, an adjacency list is nothing more than an array or an array list of lists, particularly linked lists because of how they are designed theoretically or conceptually. For the purposes of this video, we will choose the string data type as the type of data we wish to store. And we can, I will call it names, because we will be storing names later on. Obviously, the best approach would be using a generic data type. That way you can customize the data type as you see fit. But I thought I would use an actual data type for simplicity, nothing more. But obviously, if you wish to design a graph solely for integers, you will use int here. If you wish to customize it, then use a generic data type. So I will use string because I wish to create a graph or a linear tree or a genealogical chart for prophets. So I will use the names of the prophets, peace be upon them all, as the data that I wish to store. And we will need a list of this class. We will create a list of vertex. Would you import already? Sometimes it imports automatically, other times it does not. I honestly do not know how it is triggered. Adjacency list. We will call this adjacency list. Then we will add a constructor, public vertex. You do not need it to be public if you do not want to. Again, this depends on how you are designing the program. You could even put this as an inner class to the graph class. It is entirely up to you. And here we will need string name. And the usual this dot name is equal to name and this dot adjacency list. Here we will say new linked list, and that is it. Now remember, graphs are lists or arrays of linked lists. because of how they are designed conceptually, and we discussed that in the previous episode. After that, we will have public void add, and then we will say vertex. Here we will add the vertex. Add it where? We will add it to the adjacency list. Adjacency list dot add, and then we add vertex. You can rename this as you see fit, obviously. You do not have to follow the same convention that I am writing, as long as you understand the purpose of the method from its identifier. That is the purpose behind proper and auspicious choice of names. That is why I called our list adjacency list, to remind us that we will design the graph with the adjacency list algorithm in mind. Then we will add, let us see here, we will add a method to retrieve the entire list if we want it. Get adjacency list, return this dot, and you can use this if this is set to private, but obviously these are package private. Since we will create graph in the same default package, we honestly do not need these either, but normally methods are public, except in certain scenarios naturally, but most of the time they are normally public. And though this might seem rather redundant, believe apologies for that brief period of silence. I had an issue with my headset. Though this might seem redundant to you, believe it or not, the toString method is used quite extensively in full stack development. The reason I believe many feel this is redundant is because academically it is not used on a regular basis. At least from what I have seen, different institutes could have different curricula, and thus they would use different approaches or utilize different methods in their curriculum. And here we will return name. And that is it for the vertex class. Now we move on to the more difficult class, which is graph. Well, we can call it adjacency list graph. Actually, that is too long. I will just call it we will just call it graph. Now, with the graph, we will design a map, because even though it is adjacency lists are a list of lists, you could also visualize it as a map. Now, there are multiple approaches to designing this. What is being presented to you in this video is not the only approach. You could approach this particular algorithm from different angles. It is an angular approach because I will actually be recording an angular video soon, so I thought of that joke. It is hilarious. I crack myself up. Anyways, we will design map And what will this be a map of? It will be a map of the string and its respective vertex. We will call this vertices. Okay. Then we will create a constructor. And do I have a space? Oh no, I do not. Okay. Public graph. This dot vertices is equal to new hash map. Because remember, map is an abstract class. It is a class, correct? Oh, sorry, it is an interface. Either or, they have the same functionality with respect to polymorphism. Naturally, abstract classes are completely different than interfaces, but I was referring to polymorphism. They are approached in the same manner. Okay. Now we will add a vertex to the graph. Oh, for goodness sake. Now here we are actually using the vertex itself to store it in the list of vertices. But here we will add a vertex based on the datum itself. Say string name. And how would we actually accomplish this? This is why using a map is quite convenient in this scenario. Vertices.put if absent. So if it is absent, put it, otherwise no need to put it. And I hate that they call put instead of add or insert, but they chose the term, not I, unfortunately. So what will we put if absent? If this datum does not exist in the map, put it. We will put name here, and we need a vertex, so create a vertex if it is absent with this particular datum. New vertex, and here we will put the name. So we are invoking this. Sometimes I do not know why it has this pointer cursor. We are invoking this constructor now. If there are no vertices with this datum inside of them, create a new one, and this will automatically create the linked list for us. Now remember, I will draw it here quickly to refresh your memory. I will use only 3 vertices for simplicity. I have 3 vertices here, and let us say I will add an edge here and an edge here. Here is A, here is B, and here is C. What will be the adjacency list in this scenario? We will write A and then the different vertices that it is connected to. So it will only be B. This is its own adjacency list, A's adjacency list. This is a vertex, and this is a list of the vertices connected to A. What about B? B is actually connected to 2 vertices, so its list will be A, C. So B is a vertex with the datum inside of it, and AC is its own adjacency list. That is why we have designed it in such a manner to mimic this line right here. B is the vertex containing datum called B, which is this part right here. And AC, this part, this is the linked list that contains the vertices connected to or adjacent to B, right here. And then obviously here C will be connected to B only, so this is its own adjacency list. Though list is slightly a misnomer here because there is only one vertex. This is a list because it is multiple vertices, but we can change this and add an edge between A and C, so we can add A here as well. Graphs are part of the collection framework, as in they can grow or shrink depending on necessity. These two parts represent the constructor that we have designed here, which is why we are invoking the constructor here to create the vertex and create its adjacency list if it is needed. C might not be connected to anything. When we add C, might not be connected to anything. It might not have an edge. But it will still have a list, a linked list ready in case we do actually add edges to it. So the list will always be there, but it will be empty, which is what we do here, an empty linked list. Then if we connect the vertex through an edge, we add that connection right here. Now, let us return to the graph. Here, I feel I would like to change this simply to represent these. I honestly don't. Should I call this add adjacency vertices? Add adjacency vertex, perhaps? We will return to it later. Okay, so now with this, we are able to add a vertex to the graph. Okay. You may notice that graphs are actually easier to code than trees, at least from my perspective. Others might disagree with me. Adding a vertex, for example, here I could add a vertex and call this store the datum D in it. But adding a vertex does not add an edge, so we need a method to add a vertex and then apologies for that, I have an issue with my headset. Adding a vertex does not mean it will add an edge automatically. Why? Because you, as the user, need to decide which two vertices will you connect with the edge. So adding an edge must be done manually. So we will need a method for that. Add edge. Now remember, with edges, you always need 2 points, starting and finishing, or source and destination, or point 1 and point 2, point A and point B. Name them however you want. The beauty about these methods lies within the arguments. We will use the datum itself. We will not be using the vertices or the vertices here, because everything is taken care of here. So we only need to use the datum or the data type. So if you are using a generic data type, you will put that here instead of string. The same applies here. The only reason we are using string is because we set it here. But if this was T, for example, you would put T here, and T here. We will call this name 1 and name 2. or vertex 1 and vertex 2. Okay, vertex, and I will call this v1 to match name 1, is equal to, so here is what we need to do. To add an edge, you must add a vertex before it, otherwise there is no point. If I wish to connect B to D, D must exist in the graph. If it does not exist, how will I connect it? So it must already exist, then I add the edge or connect the two together. So here, what we will return on this side will be pre-existing vertices that have been added already, which means that after we invoke this, we search this map for what was added originally that matches either name 1 or name 2. How do we do this with a map? We will say vertices dot get, and here you pass the object which serves as the key, and it returns a vertex. What is our object here? String is thankfully an object, so we will put name 1. Let us pretend vertex v1 or name 1 is B and name 2 is D. B is already in the map. So when we invoke the get method on the hash map with B, the letter B, like so, it will find it. Why? Because it is already there. The same applies to vertex 2. Is equal to vertices, blah, 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 dot. Why do I keep writing a T at the end of vertex? The same applies here. D must have been added at this step before we connect it with an edge. So we are basically searching for it in the searching for datum D in the map, and then creating a vertex object or wrapping it in a vertex object, however you wish to phrase it. There is an issue, however. What if the argument is invalid here? What if instead of B and D, the user accidentally enters E, the letter E, which does not exist in the map yet? So we should accommodate for that if there are illegal arguments or incorrect arguments. What we can do is, if this is illegal or incorrect, then this will become null because nothing happened here. So this will become null. The same applies to here as well if this returns nothing, which means that if v1 is equal to null or v2 is equal to null, what do we do? Throw new, and thankfully there is an exception. See it? Illegal argument exception. If these are illegal, as in they are incorrect, throw this exception, and we will say, I forgot the double quotes, vertices, provided vertices do not exist. After we covered that, we can continue by actually adding an edge. How do we add an edge? v1 dot add adjacency vertex v2. Connect B to D. So if I do this, I am connecting B to D. So here I will add D to the list. Actually, I forgot to add D here now. And it is empty. When we created it, it was empty. But after we added the edge, here is what will happen. It will be A, C, and D. Now, since we added this to the adjacency list of B, that is exactly what we are doing here and here. But now also, we will add B here to D's adjacency list. So we will also say V2 add adjacency vertex V1. There, we have connected the two together. This will change when we actually write a directed graph. But since this is undirected, both will be connected to one another like so. So now we have successfully added the edge, not literally, obviously. We added it programmatically. That is why we use a linked list. We use a linked list because it links two vertices together. Obviously, if you wish to visualize a graph, you need particular libraries or software to actually display the image of the graph you are designing. A good example of that would be Obsidian MD. If anyone is familiar with that program, it creates a graph for all of your nodes when they are connected together. That is a visual representation of your graph, similar to this one. I will see if we could use GraphStream. I believe that is a library that allows you to design an image of your graph using Java. But I will have to research that, inshallah, bi'ithnillah, and God willing. Since we are able to add edges, we also need to be able to remove edges. If we made a mistake, for example, or the relationship changes later on, we definitely need to remove the edge. Public void remove edge. Okay. Again, we need to determine which edge are we removing. Is it between B and C? Is it B and A? Is it B and D? So again, we will be applying the same approach with respect to parameters, obviously. Here, it will be a similar approach to what we tackled or underwent in add edge. Again, vertex v1, we need to check if it actually exists before we remove it, because the user might enter incorrect names. So we need to check that the vertices being manipulated are. I apologize for that. The headset is a bit annoying with recording. I might actually need to find an alternative because I cannot record with these constant interruptions. Anyways, so we need to check if I want to remove between B and C. B must exist and C must exist, and obviously an edge must also exist. If the user wishes to remove an edge between E and C, there will be an error because E as a vertex does not exist in the graph. Get name1, get name2 for v2. And again, we will have the same problem if the user enters incorrect names here. Now here is how it will differ. That is why I said similar but not the same. Instead of adding an adjacency vertex, so let us say I wish to remove this part. What do I need to do here? I need to erase B from the adjacency list of C and remove C from the adjacency list of B. Thankfully, we designed a getter for the adjacency list of every vertex right here. So here we will say v1.get adjacency list. Let us assume this is B. Get the adjacency list of B, then remove what we want to remove, which is C in this scenario. But here we will say v2. And because we removed C from the adjacency list of B, we need to remove B from the adjacency list of C as well. So we will copy this and we will use the Zahi way all the way, baby. V2, V1. There, done. So it is similar, but not the same because of this approach here. Now, we are able to add vertices. What if I no longer need C? I need to remove C. We need a remove vertex. Just as we have an add vertex method, we need a remove vertex method. Void remove vertex. Thankfully, I did not add that stupid extra T. Okay. String name. So it will be the same approach. We will be using the datum or the type of the datum being stored. Again, if you are using a generic data type, you will put T here or whatever you called your generic data type. Okay, so what do we need to do here? C must be present in the graph before we remove it, otherwise it will cause an error. So what do? We create a vertex that we want to remove based on the data. Vertex v is equal to vertices.get with the name to check. It is the same as we are doing here. Find with this datum a vertex in the map. That is basically what we are doing. Or once you find the datum in the hash map, create a vertex for that so that we can remove it. Okay, again, we will do this, but instead of v1 and v2, it will just be v4 vendetta. And here we will simply say vertex does not exist, provided vertex does not exist if this is incorrect, hence why we are using illegal argument. Okay, excellent. What is next? What is next is if this is connected and we decide to remove it, we automatically need to remove the edge as well. You could argue, well, I will remove the edge before I remove a vertex. That is correct, but what if you forget to remove the edge? Automation is always the best solution in this scenario. So if you remove C, you should automatically remove any and all edges connecting to C to avoid causing any issues in your graph. Since edges are nothing more than linked lists, we will iterate through the adjacency list of C. Here it is empty because in the previous method we removed the edge here, but it is to check and see if there are any edges, so we will iterate through the list even if it is empty. And I will use the enhanced for loop, vertex adjacency vertex v.get adjacency list. Get the adjacency list of the vertex, which is in our scenario C. Get the adjacency list of C, vertex C, and iterate through it so that we can delete everything in it. This is how we remove edges automatically. And then we will say adjacency vertex dot get adjacency list dot remove v. What are we doing here? Since B had C already, if we find B here, we get its adjacency list and remove C from it as well. That way, we kill everything here, and whatever is referencing C is removed as well through this line right here. So the adjacency vertex in this example will be B, and C would be here. I will add it at the end so that I can easily remove it, and here will be B, and here is the edge. So if I decide to remove C, here is what happens. Create a vertex that contains C. We have done that here. Now, get the adjacency list of C, which is only B in this scenario, and iterate through it. So here it will be B and other vertices if they do exist in the list, but it is only B in this case. Whatever vertex is in C's adjacency list, get their own adjacency list right here. So here we found the adjacency vertex B. Get its adjacency list and remove C from it. Right here, remove the V vertex, which is C in this scenario, like that. And then after that, remove it from the map in its entirety. Remove V. Remove name. That way we remove this completely, like so. And then we remove this. And that is it. Now, lastly, we have one or two methods, and that is it. Oh man. Public. This is if you want to get all the vertices in your man, this is annoying. This headset is annoying. Okay. Yeah, this will probably be the last video for the day until I check the matter of these headsets. Okay. Get all the vertices. So you will simply here return array list, and here you will and here it will be vertices dot key set. So you will, oh, I forgot new, that is why it did not recognize it. And delete this part. So you are basically creating an array list of the key set which we discussed previously in the map subseries. That is if you want to retrieve all the vertices you have in your graph. What if you wish to focus on the adjacent vertices for a particular vertex? This retrieves these. But what if you wish to retrieve all of this for a particular vertex? There is also a method that we could design. Public list. Again, you will be using the data type that you desire for your data. What will I call it? Get adjacency vertices. Obviously, we will need the reference to access this from the map. That is why it is best to use the map in this scenario. You do not need to use a map. You are not forced to use a map. It simply creates conveniences for you, but you do not need to use a map. However, if you look at this design, this is definitely a map. Here is the key, here is the value, though the value is a linked list itself. Okay, so again, we will create a vertex based on the datum. Vertices.get blah, 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 the usual. And again, give me a legal argument exception if this is null to cover our bases, as they say. Then we will create an array list of this. List string adjacent vertices. You can call it list, you do not need to, or adjacent vertices because it is plural, it indicates a group. New array list. And then we will iterate through this linked list. And for every single element we iterate through, we will add it to this list. We will be returning to Big O, inshallah, bi'idhnillah, and God willing, in later episodes to discuss the differences in Big O between array lists, linked lists, hash maps, graphs, trees, and so on and so forth. But as of yet, you do not need to know this, especially since normally you will be using array lists most of the time. Obviously, this depends on your domain or your job at the company, but most of the time it is just an array list, most of the time. Adjacent vertex. v dot get adjacency list. So here we are searching, let us say for B, for example. Find vertex B, get its adjacency list, and iterate through it right here. So this will be A for the first iteration, then D for the second iteration. Add each of these to this list here, and that is it. At adjacent vertices dot add adjacent vertex. Oh, sorry. At adjacent vertex dot name, because This is an array list of the data type. So we need to put string. If we put this by itself, this is of data type vertex, but we need the name. Obviously, this needs to be private, and we use a getter for it, but for the sake of simplicity, we keep it package private or public. So now we have isolated this in an array list, and now we can simply return this one. This is obviously if you need that list separately. If not, you will not need this method, and you will not need this either if you do not need it. So this method retrieves these, and this method retrieves this based on the data type stored here or the vertex. Okay. There are two methods that I will intentionally skip because those are related to the traversal of graphs. We have seen how to traverse different data structures, but with graphs there are two forms of traversal, either through breadth or through depth. I would prefer to discuss these before we cover traversal. So once we discuss depth first and breadth first traversals, بإذن and God willing, then I will return to this and add the two methods. For now, we will skip them because we did not discuss them. Finally, I wish to design a method that prints the entire graph that I design. Public void. Oh, sorry, before that, I forgot one more method. This method will help verify that our logic or algorithm is actually correct. What is this method? The method will determine if a connection actually exists between two vertices. If the result or the return value is true, we designed our code properly. If the result is false, either there is no connection between two vertices or, God forbid, there was an issue in our code. So it will help verify that our code is written properly and correctly. Since it will be returning true or false, we will return a Boolean. And then we could say, is vertex connected? And again, because it will check between two vertices, we will utilize this approach right here. You know what? I might as well copy this. And again, we will need to get them or search for them. And again, if they do not exist, we need to handle that exception if these are provided incorrectly by the user. And simply, we will return v1 dot get adjacency list dot contains v2. Let us say B is v1 and A is v2. What we are doing here is find v1, get its adjacency list. Does it contain v2? Yes, it does, so we connect it successfully. If it returns false, that means either this does not exist or there is an issue with our code. So it is a good method to have to verify that everything is written properly. Then finally, we will print the graph. This also helps verify that everything is Oh man, these headsets. Okay, I have returned. Let us finish this quickly. Okay, since we will be handling different lists, we will iterate through them using a for loop. Oh man, so we'll say string name within vertices dot pset. Okay, and then here is what we will do. Vertex. This will obviously be slightly complex because we wish to print the entire graph. Vertices dot get name. So get the vertex from the full list of vertices, then print it. System.out.println. Actually, I want to keep all of this on the same line. You will see why in just a moment. Name plus, I want to use this format. Have the vertex, then an arrow, then its adjacency list. So space, arrow, perhaps a longer arrow. And then we will continue by creating a list of vertices. And we will call them vertices, or we can call them adjacent vertices. That would be correct, because here we print the vertex, then the arrow, and then we want to print its adjacency list, or adjacency vertices is equal to v.getAdjacencyList. So we get the list and then print it, print that list. So obviously we will need another for loop. This is to loop through the map. This the secondary for loop will be to loop through this one and then print it. Okay. Int I is equal to 0, I is less than adjacent vertices dot size I plus plus, and you will see why I used the traditional or regular for loop rather than the enhanced for loop. System.out.println, and then we will have here adjacent vertices.get with the index I. So that is why we are using this one. And dot label, because wait, I do not want it on a different line here. But why do I have label? Oh yeah, name. Okay. Oh man, I am sorry. I received a message and it seems to be urgent, so it caught me off guard. Now, if this is another reason why we used this, if, though actually you do not really need this for this part. What we need from here is the I, that is it. If, no, actually, sorry, we will need the index here as well. If I is less than adjacent vertices dot size minus 1, print comma space. This simply checks to see if we reached the end of the list or not. If we did not reach the end of the list, add a comma. If we did reach the end of the list, do not add a comma after that. So this part ensures less than adjacent vertices dot size minus 1. So the index of the last element of the array. If the current index is lower than that, add a comma when you print the list. If we do reach the last index, do not add a comma after it. That is basically the purpose of this if statement here. You do not need to add it, but you will have an unnecessary comma at the end of the list if that is the case. So it depends on how lazy or diligent you are. And then let us see, after this one, we can print an empty line. That way, when we print this, you will see a space between every line like so. That is basically this last part here. Okay. Now for the moment of truth. We will actually have to test all of this by or through the driver class. We will begin by instantiating an object of the graph class, close new graph, the one we created obviously, not from other libraries. And here let us add vertices. Graph.add vertex, and here I will add Prophet Ibrahim, peace be upon him, or Prophet Abraham, as he is known in English. Graph add vertex. Here it will be Prophet Lut, or Prophet Lot, as he is known in English. The reason I am adding this prophet is because he is, if I recall correctly, he is Prophet Ibrahim's cousin. He is the son of Prophet Ibrahim's maternal aunt, if I recall correctly. And here I will add another vertex, and that will be Prophet Ismail, or Prophet Ishmael, as he is known in English, peace be upon him. Add vertex, that will be Prophet Ishaq, or Prophet Isaac, as he is known in English. So here is what I have in mind for the graph. 1, 2, 3, 4. So one is for Prophet Ibrahim, one is for Prophet Lut, one is for Prophet Ismail, and one is for Prophet Ishaq. Okay, so here we will have Prophet Ibrahim, here we will have Prophet Lut. And for those who do not know who Prophet Lot is, he was the one that was sent to Sodom and Gomorrah, also known as the West today, or Tel Aviv, because it is the capital of you-know-what. And Prophet Ishaq. So here is what I will do. I will add a vertex between Prophet Ibrahim and Prophet Lut to indicate that they are cousins. And I will add an edge between Prophet Ibrahim and Prophet Ismail, because he is the father of Prophet Ismail. And also I will add an edge here to indicate that Prophet Ibrahim is also the father of Prophet Ishaq. And I will add an edge here to indicate that Prophet Ismail and Prophet Ishaq are brothers, peace be upon them all. So that will be the final result. If we design an adjacency list for them, it will look like this. Lut, Ismail, Ishaq. then an empty line because that is what we added in the code. Root will only have Ibrahim in the list, space Ismail will have Ibrahim and Ishaq, and finally Ishaq This is incredibly annoying. It keeps disconnecting. I do not know why. Anyways, Ishaq has Ibrahim and Ismail. So this should be what is printed. And once we visualize it, inshallah, later on, this is what you should see. Okay, so let us start adding edges. Now with edges, you must add them manually because you decide between which vertices you will add the edge, unless you have a vision for that addition. You can code it so that it is added automatically under add vertex. But with removal, you need to also factor into consideration that the user would not remove the edge before removing the vertex. So you have to consider automating the removal as well. Add edges. Graph.add edge. So I want Prophet Ibrahim with Prophet Lut, and I will copy this. Then Prophet Ibrahim with Prophet Ismail. Now remember, these must match what you added here, but we will test if I add an incorrect argument here, what happens. And here it will be Prophet Ishaq, and then Prophet Ismail and Prophet Ishaq, peace be upon them all. Okay, let us print the graph. It will be graph.print graph. Okay, Bismillah ar-Rahman ar-Rahim. Okay, so Prophet Ibrahim is connected to Prophet Lut, Prophet Ismail, and Prophet Ishaq. Lut, Ismail, Ishaq. Prophet Lut is connected to Prophet Ibrahim, Prophet Lut, Ibrahim. Prophet Ismail is connected to Prophet Ibrahim and Prophet Ishaq. Ismail, Ibrahim, Ishaq. And Prophet Ishaq is connected to Prophet Ibrahim and Prophet Ismail. Prophet Ishaq is connected to Prophet Ibrahim and Prophet Ismail. Ah, yeah, sorry, I said Ishaq here. I do not know why. You can also display the connection to check vertical connectivity. Let us print connection status plus graph dot is, and then we will put past these two. This should be true. Excellent. This is beautiful. Now let us remove vertices. So I will keep the original graph displayed. Then we will remove a few vertices and display the graph again so you can see the difference. And by the way, I just realized here the new line is to display a new line after this. It is not to create the empty space here. It is simply after finishing this line, to avoid having this appear here, we add system.out.println. So I apologize for that. It will not create an empty space. If you want to create an empty space, type another one of these. So duplicate this here. Okay, so now what we will do is remove vertices. Now, okay, so I'm sorry, I'm checking messages. I seem to be popular today. Okay, so let us remove edges manually and then remove the vertices associated with these edges. Then let us remove an edge automatically by removing its vertex. Remove edges, so we will remove the edges manually. Graph.remove edge. Let us say I decide that filial connectivity is not needed in this graph, which means I cannot have connections between siblings. So I wish to remove this edge here. Manually, obviously. Which means I will also remove this part right here and this part right here. So let us test this and see if it will actually function between Prophet Ismail and Prophet Ishaq. Then print the graph again. Actually, here it should be print graph or display graph. I prefer display over print, to be quite honest. I might actually call this display, though sometimes I use the term print because of the usage of printers. Display graph, and here I will add an empty line simply to separate between this and this, or perhaps two empty lines. Okay, or here I could say, you know what, I will just leave it as such. Okay, so this is before removal. Now watch, after removal, see, no, here for Prophet Ismail, no Ishaq, and for Prophet Ishaq, no Ismail. So the edges were removed correctly. Now, what if I wish to keep this, but I decide that I will not include cousins in my graph, only parents and children, no cousins. So I will remove Prophet Lut from the graph. Removing Prophet Lut from the graph should also remove its connection automatically. So it should remove this, and it should remove this as well. So the final result should look like this if we coded everything correctly. Let us hope so. Now I will remove this from compilation because I actually want to keep this now. Remove vertex. So here I will say graph.remove, no, not edge, vertex. And here I will say Prophet Lut. And the same approach as before, I will print the list, the graph, sorry, before removal and after removal. Bismillah ar-Rahman ar-Rahim. Okay, so you see Prophet Lut has been removed from the graph completely, and with Prophet Ibrahim, he is not in the adjacency list either. So this is correct. And also I should remove this as well. And that is it for this lecture. Inshallah, bi'idhnillah, and God willing, in the upcoming videos, after I resolve the issue with my headset, that is, we will cover adjacency matrices for graphs, and we will cover directed graphs as well. Inshallah, bi'idhnillah, and God willing. And then I believe I will end the data structure tutorial series with what was it called? Big O notation. We will see the differences in Big O, whether temporal complexity or spatial complexity, across different data structures. And I believe that covers data structures. Unless there are others that I have missed, I believe I covered everything. But it will not hurt to review and add more if there is more to add. And that is it for this video. I hope this lecture was helpful and beneficial to you all. Enjoy. Enjoy the rest of your day, everyone. Be safe, take care, and peace be upon you all. Wassalamu alaikum wa rahmatullah.